Hello everyone, welcome to Stat Harbor Analytics. Today, let's talk about causal inference. In statistics, one of the most important distinctions is the difference between association and causation. Just because two variables move together does not mean that one causes the other. For example, imagine we observe that people who take a certain treatment tend to have better outcomes. Can we immediately conclude that the treatment works? Not necessarily. Maybe the people who received the treatment were younger. Maybe they were healthier at baseline. Maybe they had better access to care. So what we observe in the data may reflect not only the treatment effect, but also systematic differences between groups. That is exactly why causal inference matters. Causal inference is the field of statistics that tries to answer questions like, what would have happened if the same person had received the treatment versus not received it? What is the effect of an intervention, policy, or exposure? How can we learn cause and effect relationships from imperfect data? At the heart of causal inference is a simple but profound idea. For each individual, there are multiple potential outcomes. One outcome if they receive the treatment, and another if they do not. But in reality, we only observe one of them. We never observe both worlds for the same person at the same time. This is called the fundamental problem of causal inference. Because of that, causal inference is really about building credible comparisons. In a randomized trial, treatment is assigned at random, which helps make groups comparable. That is why randomized experiments are often considered the gold standard. But in many real-world settings, randomization is not possible. So we turn to observational data and use methods designed to reduce bias. These include matching, where we compare similar treated and untreated individuals, and weighting, where we rebalance the data to mimic a randomized experiment. Outcome modeling, where we predict outcomes under different treatment scenarios, and more advanced approaches like doubly robust estimation. But methods alone are not enough. Causal inference always depends on assumptions. Some of the most important are exchangeability, meaning no unmeasured confounding, positivity, and consistency. If these assumptions fail, even sophisticated methods can give misleading answers. So causal inference is not just about applying a technique, it is about carefully aligning the question, data, design, assumptions, and strategy. In the end, causal inference helps us move from what is associated to what would happen if we intervened. And that shift is essential in medicine, public health, economics, policy, and decision-making more broadly. Because good analysis does not stop at description. It tries to answer the deeper question, what actually makes a difference?